okay, so Steph told me, yeah, okay, show something around the virtual machine. And then, and then I saw everybody was presenting things about testing. So I said, okay, no, I want to show things about testing too. So actually, the presentation will be a lot about testing the virtual machine. And I will show some stuff that we are doing with all the other guys. So you will see. The names there, we don't care. So actually, we are a lot in the team. So we have Steph that is working with us. Noel that is working as an engineer since a couple of months. Now he's going to start a PhD. There's no Sufyan there, but he worked a lot on the VM. So he did a lot of improvements. There are people that do some stuff on the VM from time to time. So there's a lot of people there. I'm not alone. I'm just here, the face that so you can throw tomatoes. I have this small image of what is a virtual machine. So this is really schematic. So the virtual machine is just a kind of, it's a program. It's like any other one. But it's a program that executes another program. So you will give the virtual machine some code to execute. And this code, we are going to say it's cold. Yeah? So eventually, this maybe it's executed by a slower execution engine like an interpreter. And this interpreter will detect, look, this code is executing from a lot. So maybe you want, so this is hot, and you want to optimize it. And then where it is going, the virtual machine is going to compile it. OK, thank you. OK, so maybe try. This will probably not work. So it's going to compile it. So this has a pointer? Yes. OK, so we're going to, the virtual machine will decide to compile some pieces of the code, and then to execute directly in compiled code. And all these share the same managed memory, so garbage collector and stuff like that. So this is where we are. This is our world. And a couple of years ago, we had to extend this thing to support ARM v8, so ARM 64 bits for the new Mac machines. And there are a lot of Linuxes now that are running on this, and or Windows, even Windows machines. So we had to extend the compiler backend to run on this thing. Yeah. So one of the things that happened is that we wanted to test this. Yeah, we wanted to make sure that actually this was running and not die in the process. So we started to think, OK, how can we test on real hardware? And the thing is that we didn't have any real ARM 64 hardware at the time. So we started to think, OK, how can we work on a partial implementation of the compiler that we can start running and doing some like TDD style without having a full VM that we need to compile and run. So can we do it iteratively? Can we do a partial implementation? How do we do it when we don't have the hardware? And also, if every change that we have to do, we have to wait 5 minutes until the VM compiles and translates to C and blah, blah, blah. So it will be very slow. And also, I don't know how many of you experience reproducing bugs in the VM. So it is a very demanding task. Because maybe the bug, you will hit it once the VM has executed a couple of million of instructions. So if you're going to step, it will take a lot of time. If you have to put a breakpoint, that will slow down all the millions of iterations and cycles that have happened before. So it is really slow to actually reproduce a bug in the VM. So we already had a simulation environment. The simulation environment runs in Pharo, so the virtual machine is entirely written in Pharo. So we have the interpreter, the GC, the JIT compiler written in Pharo. Eventually, of course, this gets transpiled with slang to C, and then we compile that, and that is the production VM. And in the simulator, we instantiate a heap and a native code cache, and then we run stuff in here. So it's a bit slower than the real machine, but actually this in here we can use all the tools that we use in Pharo. So we use the Pharo debugger, the Pharo browser, and stuff like that, all the navigation tools that we have. And also the things that this transpiler does a lot of transformations that are really specific to interpreters or optimizations. So what happens here is that maybe these transpilation or transformations, they make the code not so easy to debug. So we extended in the last years the simulation environment to use machine code simulator that is called Unicorn that supports a lot of different architectures, so it's really handy for that. And with a disassembler that runs on LLVM that can disassemble everything. So this is just anecdotal, but this is the tools that we are using every day to work on the VM. And OK, we wanted to make the ARM v8, and we extended it with a testing infrastructure. Yeah? So I'm going to talk a bit about how this testing infrastructure looks like, and what are some of the design guidance that we have. So I will show it with an example. So this is a test. This is probably the simple test that we have in our JIT compiler, in the JIT compiler. So this test is testing that if we compile the push constant 0 bytecode, so there's a bytecode instruction that pushes the constant 0, that it will actually push the small integer 0. Yeah? And how this test has 3 lines of code. So it compiles this bytecode here, and then we run the generated code, and then if we pop what is in the stack, we want to get the integer object 0. Yeah? So we can actually, this was probably not the first version or the first iteration of this test. We learned a lot while writing it. So the first thing is that, so to have this running, we have a lot of reusable components that we are reusing across a lot of tests. So we have, for example, trampolines and stub compilation. We have the heap initialization that may take time, and it's really time-consuming from a human to actually initialize the heap for every test. So we have a lot of fixtures and reusable components for the tests. We have an internal DSL, let's say, for compiling stuff. So we can compile stubs. We can compile here, for example, a single bytecode. We can compile also intermediate representation instructions directly. We can also run directly the generated code. We have many ways to actually execute the generated code. For example, you can run all the code until it returns, or you can run all the code from one place to another. So depending on what kind of test you are running, you want to use different helper methods in here. So the other thing that actually we do a lot is that we do black box testing. Actually, most of our tests are black box tests. So here, for example, how does the black box testing idea materialize in this test? So the first thing is that this test is about observable behavior of the VM. So we don't test that we generated the right instructions. Yeah? Because actually, if we do that, it will be really complicated to assert for every different architecture. Or even if we change the compiler later to generate some other kind of instructions instead of these ones, so we have to update all the tests that we have. So actually, this test is really looking at observable behavior of the compiler. It is reusable in different backends, and it's resistant to changes in the implementation. So this is, we have really few tests that are actually looking at what the compiler does inside. We only do that when we really need to test some particular compiler component. For this run generated code here, so we are using cross-compilation and cross-execution, what I call it. So we are using Unicorn actually to make our test. So it is hardware independent. We run it on different architectures, for example, ARM, Intel, RISC-V, 32, 64 bits. And we use parameterizable tests for that. So this test actually runs for a lot of different combinations. Actually, it is running every time that we do a commit on the virtual machine right now. So while working on all this testing infrastructure, we learned that, of course, everybody knows that there's no silver bullet. But there are different ways to test and debug the VM. So we learned that simulators are cheap. So we can run stuff in a simulated mode, but they are not 100% trustworthy. So because they are not very precise, sometimes you will hit bugs or design decisions in the simulations that will make it shift a bit from reality or from the hardware because it's faster to simulate. Yeah? There are things that our tests are really fast to run, but sometimes we want to run full execution. So we want to restart the VM and say, OK, execute this program. This actually helps us a lot to, so either in the simulation or on real hardware. So it is expensive to run, yes, but sometimes it helps us to discover new testing cases, so to get the real scenario to test. So our unit tests really help us to exercise specific scenarios, and we use the full executions to cover not yet covered scenarios. So sometimes when we have a bug in the CI, we don't know what the bug is. Of course, if we knew what the bug is, we would have a unit test for that. So the thing is that, OK, once we find the bug, we try to reproduce it, and we build a unit test for that. So with this, we have this kind of workflow for testing the VM. So we do unit testing a lot. So we are here a lot. And from time to time, so we enhance our infrastructure, of course. And from time to time, we go over full simulations. Yeah, so this one is times the thousands, and this one is times hundreds, maybe, or even less. Yeah, so we do full simulations. And once our full simulations are good, and we say, yeah, look, this looks like it works, OK, then we go to real hardware. Because the hardware actually, it has the slowest experience. So you have to compile the VM, you have to run, and then you have to debug on GDB to get the real thing, to move on and to find the problem. Yeah. So this is kind of how we work. And with this infrastructure, we built since June 2020 around 450 tests on the interpreter and the garbage collector, and 580 tests. So these numbers are from May 2021. But we have a lot of handwritten tests like this. Yeah? And they are parameterizable in 32 bits, 64 bits, ARM, Intel. Now there is the RISC-V that I will talk a bit later. So we had at this time around 1,000 tests that were handwritten. So the question was, OK, is it enough? And one of the things that we started doing last year is to think about, OK, how can we automatically generate tests for the VM? Yeah? So we have people that will send code here, any code. OK, and I want to ensure that the interpreter and the compiler are working well. So can I automatically generate tests for this stuff? Now, generating tests for a compiler or for something that executes code, it's not really easy. Because, for example, if you are testing a compiler, chances are that if you are going to generate just random text to send the compiler, chances are that 99.99999% of the tests that you are going to generate are just going to be thrown away and rejected by just the parser. Yeah, because you are going to generate a lot of bullshit that doesn't even parse. So if you want to test, to arrive, to execute something, you need to generate already something that parses, that types well, something that actually has some semantic correctness. Yeah? And you want also that all the tests that you generate, they need to be covering a lot of different regions and branches and paths in the execution of your code. Yeah? And once you generate the test, OK, let's say that we can generate a lot of tests that are semantically correct, and then you say, OK, they are testing valid scenarios. OK, how can we automatically create the assertions for those tests? Yeah, I can generate programs that I can compile, and I know that they are different. They cover different paths. So how can I determine if they are actually being correctly executed or not? So for that, we came with a solution that this is something that we are using right now, and we are improving it still. We will improve it in the next years. OK, can we maybe automatically guide the generation of tests from the interpreter? Yeah. The idea is that, OK, I take the interpreter. I automatically generate valid tests from the interpreter. And then I'm going to execute those tests that I generated, both in the interpreter and the compiler. And once I have that, I can compare the results. And of course, if there is a difference between the results from the interpreter and the compiler, it means that there is a bug in one of them. I don't know which one. Yeah? But then we can actually look at the errors, and we can see, OK, where is the problem? Why? So what are the insights behind this solution? So first is that the interpreters are actually kind of executable semantics of the language. Yeah. So I'm going to show you an example now. But the thing is that since these are kind of executable semantics, we can use techniques like concolic interpretation or concolic execution over the interpreter. So somebody knows what is a concolic executor? 1, 2, 3. Okay. So I'm going to really go fast on that. I don't have the presentation. Okay, I have time. So I'm sorry, I am in between you and the lunch. So, so let's say we have this bytecode. So this is the bytecode that executes the add. Yeah. So when you want to add two numbers, so when you have the plus, the message plus, actually this gets compiled or executed using this bytecode implementation. So what does it do? It takes the receiver and the argument of the plus message. It checks if both are integers. If both are integers, then I can try to add them up using here the sum. And then once I add them up, I have to check that there was no overflow. Because maybe I cannot represent the sum of the two integers as an integer. Or as an...
This is C.
Yeah, this is C semantics. This is a small talk code that has C semantics. Let's think about like that.
So we don't have infinite numbers. We have numbers that overflow.
Yes. So if...
It looks like Pharo, it is not. It is C.
If you want, so here, if you want to handle the overflow and create a big integer with a boxed representation, you have to manage it yourself. Let's say it like that. So here you do the sum, you check for the overflow, and then if there was an overflow or one of the two arguments was not an integer, then you have to send a message send. And then the runtime, the Pharo runtime will manage the code. So that's why in primitives you have a fallback code. Like that you can have some code that is executed when something fails. So here actually the fallback is to do a message send. Otherwise, we can just actually, that means that we did a successful sum, and then we can continue. We don't have to do a slow message send. Yeah? So here we have somehow some part of the semantics of the language. We are checking that both things need to be integers, that the sum should not overflow, and we need to see what we need to say what happens if this does not hold. So if in that case, we are going to execute a slower path that is just executing a message send. For now, believe me, this is faster than doing a message send. So what if we have a way to execute this code and track this stuff? Yes? If we can track this information, then we can automatically generate tests for this code here. I will leave that to you, that idea there. So the second idea behind this solution is that both the interpreter and the compiler share semantics. So they should do the same. One should be faster than the other. Yes, one should generate a more efficient code than the other. But they should do the same. So this same thing that happens with the integers, doing that check for overflow, blah, 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 check that they have the correct type, and send the message. And so both should do that. Otherwise, your code will not be correct. So that means that we can have this idea of differential testing. Differential testing is the idea of compare the results of two executions of things that have similar semantics. So how does this work? Actually, here you have the same code as before. So here you have a machine code-like representation of what the compiler does for this code. So here you can see that actually they do the same. So here we can have to check that these two guys are integers, and here we do that too. We have to check that there's no overflow, and here we have to check the same. And here, otherwise, we have to do a message send. Yeah. So the compiled code, even it's not in the same representation, it doesn't have the same data structures and so on. So this one will be faster, and it doesn't have the same shape, but they do the same thing. So that means that we can use them to do this differential testing. Yes, Steph.
What you have on the right, this is the JIT.
This is what the JIT compiler uses, or is a representation like this is used by the JIT compiler, yes. So this is an intermediate language that is used by the compiler. Based on these ideas, okay, we build this concolic tester. I will explain you how this concolic thing works with a smaller example. So the idea is that we can guide test generation by looking at the implementation. Yeah, if we have the implementation of something, we can use a white box approach, look at this and say, okay, these are the tests that you need to execute. So here in this code, we can see easily that if x is bigger than 100 or smaller or equals than 100, then we have different cases. And if y is equals to 1023 or different, we have different test cases too. Yeah. So how does a concolic executor work? So the concolic executor will execute this program at the same time concretely and symbolically. I will not go into the details. What that means is that we are going to execute this program with real values. And for each of the executions, we are going to execute it many times with real values. And for each of the executions, we are going to track the different conditions that happen. Yeah? So the first time, let's say we start with some random value. So we say x and y are 0. Yeah? Then we execute this thing, and we see, look, x was not bigger than 0. So x was smaller or equal than 0. And then we exited. So that's OK. Now, if I want to generate another test case, I can just take this condition here. I can negate it. And now, if I generate values satisfying these conditions, I will generate values that will walk through a different path in the execution. So if I give this to a solver, there are a lot of mathematical solvers, equation solvers there written in a lot of languages. So I give this to a solver, and then it will generate, OK, maybe you want to try with x 101 and y equals 0. So if we do that, then, look, now your program walked through this path. X was bigger than 100, and y was different than 1023. So now let's do the same. What happens if I negate the last condition? So now we have to generate something where x is bigger than 100 and y that is equals to 1023. So if we execute that now, we went through these conditions. There's a bug in here. And now we finished. Actually, there are ways to determine when you have finished, and that's all. So we can use this, actually, as the characterization of what are the different test cases that we have to execute. So we have actually a concrete characterization of the inputs to generate tests. And we have an abstract also representation of what are the different inputs. Now, some numbers. So we use that on the VM to do so differential testing between the bytecode interpreter and the different compilers that we have. We have the ones that we use in production, but we have some other ones that are there for research and stuff like that. So we tested not only the compilation of bytecodes, but also the compilation of primitives. And to make the story short, we generated around 5,000 tests, and we found 500 differences. Yeah? So OK, funny. We looked at each of those 500 differences by hand, one by one. We found that actually most of them were caused by 91 different causes. So many of them have the same cause. And we could organize those different causes in 6 categories. So sometimes we had missing type checks in the interpreter. Sometimes we had missing type checks in the compiler code, in the compiled code. Sometimes there were optimization differences. So for example, the interpreter was more optimized than the compiler, or vice versa. Yeah? There were some behavioral differences and some missing functionality and stuff like that. So the funny thing is that from actually this one, if you don't pay attention, actually you can cause segmentation faults when you have the wrong, if you don't have the type checks. Yes?
What do you mean by optimization difference? Optimization should have no consequence on the output, or what kind of optimization?
So the question was, what do I mean by optimization differences? So I will do a step back, and I will not claim that these are bugs. Yes, these are differences. So this approach finds differences in the behavior of both. Now, maybe some of them are bugs and some of them are not. We found these optimization differences. For example, the compiler, if it sees that the arguments of the plus are constant, it will do the constant folding automatically, while the interpreter does not do that. Yeah? So some stuff like that happen, and our approach detects it. That it doesn't mean that it's a bug or a problem. So, but I think that it is worth it to actually document these different optimization differences.
They led to different results?
They don't let, sometimes they can let, for example, that a non-optimized case can go through a message send. Because Or for example, actually the case that happens is that there is one of the compilers that don't do the optimization of the plus. It just does a message send without trying to check if both are integers and then trying to do the addition directly. Yeah. So there is a behavioral difference. There's one that makes always the message send, and another the interpreter that tries to do the smart addition before, which is called a static type inference, static type prediction.
There is an important aspect that you have to code the compiler, and that can be super. Sometimes it is not worth to optimize something that will be in any case slow. So it means that from the compiler perspective, there were some choices that said, okay, you know, if I go to the fast path, I want the fast path to be super fast. The slow path, okay, let's jump to the interpreter because you have also constraints. You have constraints of the size of the assembly that is generated. So you can also say, okay, I don't want to fill up the assembly cache for things that will be maybe 1% of the time used. In that case, we fall back to the normal, the slow path, and those kinds of things.
Okay, so
yes.
Are these the differences from the output, or is it just the differences by manual inspecting?
These are the different.
Are taken?
No, these are the differences in the output. Yes. These are differences in the output. Yes. What is this missing functionality is the question. So when doing this, we found that there were some things that were implemented in 64 bits that were not implemented in 32 bits for some architecture. And since we were not building that architecture or running it all the time, but because now 32 bits actually is not so common, so our approach has just found, look, here you have an exception if you go through that path. And while the interpreter did not.
So just a remark, because so what you show is that this has been presented to the best conference in programming language design. So we didn't tell it, but
I don't care.
The idea behind the scene is that what we would can we go to the picture where you have the compiler and the.
Wait. Okay. I'm going to this picture. This picture?
Potentially, yes. So you see the compiled version. Ideally, we want to see if we can get rid of it.
No, okay, no. No. Yeah,
yeah.
Okay, but that's for another talk.
That's another talk, but this is just to take a picture.
We don't want to get rid of the compiled version. We want to get the compiler automatically generated. That's another step.
So our idea is, can we take the interpreter and generate the code that generates the assembler?
Okay.
And the idea is that if we do that, we need to have tests to know, because we can generate things that would not work.
Oh, here. Okay, I'm here. So, questions? Okay, I can move forward. So, the other thing is that, okay, this approach was surprisingly practical. Also, it runs, so test generation runs in around 5 minutes for 5,000 tests. So that means that we can run it in the CI maybe once a day or something like that. It's not time consuming. It doesn't take days like other approaches that do test generation. And once generated, running them, it's around 10 seconds. So it doesn't do anything. So the graphs are nice. I like the colors. So here actually we show the average time of running the different test cases. The nice thing to see this is that native methods, so here the primitives take longer to execute and to generate because of course they have more paths to explore. So that means that there is a kind of correlation between the simplicity of the bytecode and the number of passes that we are going to generate, and the number of bugs that we are going to find also. Because here we found a lot of more bugs than in the bytecode, because the bytecode is much simpler. Differences. Yes, sorry. We also, so if we found less differences, we have less bugs. So you can go and check the article. This is an article in PLDI this year, if these kind of topics interest you. So is that all? I have time. I went fast. There's some other stuff that is going on, so we are not just testing the VM. We are also working, actually, it's Quentin Ducasse with Loic and Pascal Courtrai. Pascal Courtrai, okay, with an R. Yes, that are working actually on a RISC-V port. I don't know who knows what RISC-V is. So it's a new kind of architecture that has open source specs. So you can generate your own hardware, and you can create extensions for this thing. So it's kind of the next thing also regarding security. So they are using our test harness suite to help with the port of RISC-V, and they are working on this actually to make security enforcement. So this is something that is going on the VM. There's also some work from Nicolas there. So if you want to talk about with him about parallelization at the instruction level. So he's working on single instruction multiple data extensions for the Pharo VM. What is the idea? The idea is that there are some instructions in the most modern CPUs that allow us to do some operations in parallel. Like for example, here you can do an addition. We make the difference between scalar and vectorial instructions. So a scalar instruction will do the addition between two numbers, while the vectorial instruction will take a bulk of numbers, and then it will do each of them plus, 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 plus in a single cycle. Yeah? So this has several usages, mainly for numerical computations and stuff like that. But also it can help optimizing our speeding up stuff like object allocation. So he's working on extending Pharo to use these kind of instructions. We are kind of exploring the design space. Like for example, what happens if you use these kind of instructions in primitives, or you expose a vectorized bytecode? Yeah. So what are the different constraints that we have? For example, primitives are kind of specialized. So if you only rely on primitives, it means that you need, for every case, you need to have a special primitive that uses these kind of instructions. So they are less composable. They are kind of really monolithic, but they are faster because there are less checks in there. So you don't need to check bounds of arrays every time. On the other hand, if we are working on vectorized bytecode, that kind of helps you compose different bytecodes that work at the vector level. And they are safe. They need to be safe because the design of Smalltalk and Pharo is that we need instructions to be safe. But they are safe at the expense of speed. So here, for example, you can see in the different colors is that in blue, you have the primitives, the speed of a primitive, the speed up ratio here, and the throughput. Here in red, you have the scalar implementation, so the one that we have by default. And in yellow, you have the vectorized bytecode. So you can see that primitives are faster, of course. Both of them are faster than the scalar one. And we are seeing this kind of gaps. So we would like to have less gap in here. So we are working on this kind of stuff. We are making a lot of tools for debugging too. So Nahuel there, he's working on a new compiler that is going to do a lot of things. We don't know yet. And in this compiler, we are working a lot on a new intermediate representation. So this is the model that we have of the code. Yeah. So here, actually, each box is a sequence of instruction, and inside the little boxes of color with color there are instructions. Yeah. So we are working on a representation of code that helps us doing optimizations, track dependencies between instructions, and stuff like that. We are also having, for example, machine code debuggers. So we make our own tools every time to help us get to speed with the VM development. We also have worked along a lot with Sufyan, for example, in the last 2 years. So one of the things that happened is that the VM, for example, had an optimization that was hard-coded in the code of the VM. That was called variable localization. Yeah? The idea is that you have a variable like the stack pointer, and then that variable is made is duplicated inside the interpreter loop for performance reasons. Now, that variable was it was duplicated by hand, and that means that all the code that had to go through the stack pointer needed to, first, we needed 2 versions of each function or each method that uses the stack pointer. For example, here we have internal push and push. One uses the local stack pointer, another one uses the stack pointer. And this was kind of duplicated code. And the other thing that happened is that the developer, the VM developer, should every time know how this was going to be generated in C code to know which version he or she should use. So every time that I had a new student or somebody that was asking me, OK, what does it mean, the internal push and the push? Well, so I didn't want to explain it anymore. So one of the things that we did is to do automatic variable localization, to do the optimization by automatically. And first, that made simpler the VM code, simpler to explain to anybody. And the other thing is that now we can also measure different configurations. So this was a small paper. But the point is that we saw, for example, that here the red line is the baseline. So this is the VM without any optimization that now we can generate because now the optimization is applied automatically. And then there are 3 different variables that are usually localized. And we tested different configurations and combinations of optimization. And we saw that actually there was a trend. So at least in my old Intel x86 here, so these benchmarks are not very serious benchmarks, but actually they show this trend. That is nice. And now the thing is that we can do these kind of experiments now. So we are simplifying the code base while not losing performance. I had another graph that shows the manual optimization against the automatic optimization, and we see that there's no difference. So we can do it automatically and remove the burden from the developers and put it to some code generator. The other thing that we were looking at some point, so this one is a nice story. So the people from Moose came and said, look, loading Moose in Pharo is slow. It was taking around 4 or 5 minutes. Yeah? And then Pablo said, OK, let me check. I will generate a special version of the VM where we can expose events. And we can introspect and see what the VM is actually doing. And here, what you see in the blue line, so here is 100%. Here you have 50. So this is the occupation of the code cache. So here is the machine code. So how much machine code do we have in the code cache? So you see that eventually it will go to almost 100, and then it goes down. So we have a garbage collector for machine code. And in red, what you see is that we compact this. We are garbage collecting the machine code. Yeah. So we have a lot of collections in those 4 minutes. So one of the hypotheses that we had was, OK, maybe we are trashing. Yeah, we are generating machine code that when we are discarding and then we are regenerating. So we are putting a lot of effort on compiling code for nothing and discarding code again. So then we started testing different configurations and see, OK, what happens if I make this code cache bigger? Yeah, so here, up to, from the default is 1 megabyte, 1.5 megabytes. And we tested different configurations up to 10 megabytes. And we tested also different young space configurations. So we have the GC that is split in different generations, and the younger generation where the objects are being born. So we tested with 1 megabyte, 10 megabytes, 100 megabytes. Yeah. And one of the things that is, so here you see the, so this is the time that it took. So that means that higher is worse. Yeah, more time is worse. So we want to be here. And the thing is that, OK, adding space in the code cache actually made it larger. So actually, it made it slower. Yeah, so you have more machine code. You have less trashing. Actually, we have the graphics. I don't have them here. But you have actually less trashing, and still it's slower. So maybe this configuration is not good. So actually, the thing that we observe is that we don't want to have a long code cache. We want to have maybe a larger young space. And why is this? So after some more profiling and debugging, so we saw that actually what happens is that every time that you want to run a garbage collector, you have to go through the code cache because the machine code has references to objects. So that means that you have to somehow decompile the machine code to find the references and then to track them and mark them. So that means that making this larger, it gives a lot of work to the garbage collector. So, and this we could do because we could extend the VM and make tools on top of that. Some final words. So these are some of the projects that we're working on and improvements that we're doing. So we're hiring. We are looking for people, young or not so young. If you are interested in compilers, interpreters, memory management, security, come and talk to us. We have engineer positions, PhD positions. So if these are the topics that you like, then I'm open to discussing. Even if you don't want to get hired and you just want to discuss. So thank you very much. I think that we can go to it. Yes, Casper.
This surprising discovery of garbage collecting the bytecode, do you know if there are similar experiences from the VM or .NET platforms regarding these things, or so?
There is some work on finding, sorry, what is the question is if there is some related work on how to manage the code caches, the machine code cache. Yeah, so there is some work, not so much, at least not studying the relationship between the code cache, the machine code cache, and the garbage collector. So most people will actually, so the related work will study how to share the code cache between different executions, or how, for example, to organize the code in the cache. So for example, you can reorder the code in the cache to enhance locality and stuff like that. But there's really few work on how to design this code cache so to, for example, avoid these kind of problems. Steph has a question.
No.
Yeah.
I just have a final message. The message that is underneath, this is that yes, we really take care of the virtual machine. And we will have really a full team. We have a project that is starting, and we will really continue to work in this area for the next decade. So, from the Pharo perspective, you know, 5 years ago it was really an uncertain point, and now we are really confident that we can really, you see, apply software engineering techniques to control the complexity of the system, and then to really go further. You know, we would like to see can we work on parallel execution and things like that. So for me, this is really a super important message, is that we remove this problem for our path. And we can control the virtual machine, and we will continue to work on that. So.
If you're interested, on Thursday there's another presentation where we're going to talk about a new image format, permanent space, and things like a faster startup and saving images. So that's all.